Let's do problem 3 on page 241. Here it is in your book. Right here. Let me zoom in so you can see it. Okay. So it says a person with a remote mountain cabin plans to install her own hydroelectric plant. A nearby stream is 3 meters wide and 0.5 meters deep, and water flows at 1.2 meters per second over the brink of a waterfall that's 5 meters high. The manufacturer promises only 25% efficiency in converting the potential energy of the water earth system into electric energy. Find the power she can generate. And it says large-scale hydroelectric plants with a much larger drop are more efficient. Okay. And in fact, this is actually a pretty real-world problem, because there are people who install very small hydroelectric generating plants, for their personal use up there in the mountains. So here's what's given. Actually, let me zoom back out. So here's what's given. Here's our water, and it's 3 meters wide, the stream bank, and then it's 0.5 meters high, and the water's moving at 1.2 meters per second, and it's going over the falls, spinning a turbine, generating power with 25% efficiency, and the water drops a height of 5 meters. So we want to know what's the power output, P out, for this generator. It doesn't say pout, it says P out, power out. All right, well, let's solve it. The power out is equal to 0.25 of the power in. Okay, this is the power that is received by the generator, to make it spin. And it's only able to convert 25% of that into electrical energy. So we have to figure out what this power in. Well, remember what power is. Power is energy per unit time. Okay, well, how much energy does a 1 second's worth of water have when it's up here? Well, you would say, okay, the energy, this is potential energy, and the gravitational potential energy that this water has would be mgy. Okay, and that's the height above here. I put a negative here because that's the displacement of the water's negative, but it's 5 meters above the generator. So we would have to take this potential energy and divide it by time. Well, what we need is to talk about mass. We know what G is, and we know what Y is, but but this mass per unit time, M over T, we need an expression for that. Well, we do have an expression for volume per unit time. If you think about how far the water goes in 1 second, well, it's 1.2 meters, which actually on this scale would be, I don't know, a certain volume of water, but it's in 1 second, so you just make it per second. So the mass per unit time is equal to the volume, well, the density, and rho, by the way, is the density symbol that we use in more advanced physics classes. Rho is the density of water times the volume of water, because remember, density times volume is mass, but we have to have per unit time. And well, what is the density of water? Well, it's yeah, and you have to kind of know this. I mean, it is a gram per cubic centimeter, But in physics, we don't use grams and centimeters, we use kilograms and meters, and it turns out to be 1,000 kilograms per cubic meter. That's the density of water, that's rho. Well, now what is the volume of water times volume? Well, it's 0.5 meters, right? That's our height, and our width is 3 meters. But what's our, well, this is the depth and the width, and then, I don't know, whatever this is, this third dimension out here. We're going to call it 1.20 meters every second. And that takes care of my time. This is the volume that goes by every second, the volume of water that tumbles over the side every second. And so now that includes our t, our time. So the mass per unit time, and notice that meters, that cancels, the meters cubed, and we have kilograms per second, which is mass per unit time. And so we have 1,000, okay, times 0.5, times 3, times 1.2. And you get 1,800 kilograms of water going over every second. So this is basically the mass over time, and we plug it in there. And we know what gravity is, and we know what y is, so now we can figure out our power in. This is power in. So, so we can now say, well, the mass over time is 1,800 kilograms per second times g, and g is 9.8 newtons per kilogram, and then our y is 5 meters, and so our power in, we have to multiply all that out. And we get 88,200. Now what are our units here? Well, a newton times a meter, that's a joule. That's really a joule of gravitational potential energy going over the side every second. So a joule per second is a watt. So 88,200 watts. Now that's how much power is delivered to our generator. But the generator only turns 25% of that into useful electrical energy. So let's multiply that by 0.25. That's 25% of 88,200 watts. And so our answer should be 22,050 watts. And, well, let's check our work. Number 3. And it says 22.0 kilowatts. So 22.0 and this 5 is just a round off difference watts. So yep, that's good. So we can put a star next to this guy. All right. I would probably round it to 22.1 watts, and they may have kilowatts. So you can say the power is equal to 22.0 kilowatts. I think whoever did the problem for the book, they for the book's answers. They did it a little tiny bit differently and rounded it off slightly differently than I would. I would probably put 22.1 kilowatts, but this is what the book got. But this is the correct solution. And that is all.